Okay, I start. So here we're going. So in this lecture we'll look at radiation from a dipole. Okay. So oh, you're right. So my bad. Thanks for reminding me of that. That's why you need an audience. Huh? Okay, how's that? Okay, so we're going to look at radiation from electric dipole. So the situation is that we're going to have some coordinate system, and at the origin, okay, we will have a dipole orientated in the positive z direction. Okay, situated at the origin. Okay, so dipole will be some charges that are separated by some really small distance. Okay, and the actual amplitude is the direction dipoles in the az direction, but the amplitude is time varying. Okay, and it's given by p sine omega t dash. Okay, so at one instant it's orientated like that, and a short time later it will be the reverse. Okay, be a sine function. Okay, and we're looking at we want to find eventually we want to find the E and H fields in space due to that oscillating electric dipole. Okay, and to do that we need to find we're going to find A of R first and phi, the magnetic vector potential. Okay, so we're going to find that position R in space. Okay, out here. Okay, so that means we're actually interested in finding what the dipole is at the retarded time. Okay, because remember we always have to allow a bit of time for any changes in this dipole to propagate distance r. Okay, up to the point that we're going to measure it. We're interested in finding it exactly. Why it's not working? Okay. So so in this system, so we've got free space. We don't have J, we don't have any currents, and we don't have any magnetic dipoles. Okay, may not have charge, but which equation could we use? But we do have a dipole. Okay, a single dipole at one point, the origin. What would be the easiest method or formula that we could use to find, eventually find the E and H fields? Okay, what would you choose? Anyone want to hazard a guess? This one? Which one? Okay, yeah, this one. It happens to be this one's probably the most relevant. Okay, because we don't have this component, we don't have currents, and we do have a polarization which is changing with time. So we do have a PDT, but it's only at one point. Okay, at the origin. Okay, R dash. Okay, at the origin. So that makes this integral very easy. Okay, because you just have an integral just contains the integral at a single point. Okay, so that makes it very easy. Okay, so so the one to choose happens to be this one. Of course, we don't have rho, we don't have J, we don't have M, we don't have Q, but we do have the P. Okay, and at one point as well. Okay, so we can do that. Okay, and so we can do that integral. Okay, and if we do that, as I said, it's very simple because we only have the dipole at one point, which is at the origin. Okay, and so that integral for a position R. Okay, at position R with theta in spherical coordinates at a particular time. Okay, is going to be this. Okay, is that clear? Okay, because R minus R dash. R dash happens to be at 0, which is the source. Okay, so R minus R dash, the magnitude of that's just R. Okay, the distance from the origin to the point where we're observing AR. Okay, and we can take the time derivative of this P. Okay, will be just mu naught omega P cos omega t, and we can replace that retarded time T dash by the actual time and the position R. Actually get in the actual T form of T. Okay, so that's our magnetic vector potential due to the dipole at the origin. Okay, now that's in rectangular or Cartesian coordinates. Okay, of course we had the dipole orientated in the AZ direction. We can convert that AZ to spherical coordinates. Okay, so we can put it in terms of the unit vectors in spherical coordinates, which are AR, A phi, and A theta. Okay, so that's not in the formula sheet, so you don't have to do that in the exam, but you can look it up in the book. Okay, and you can find that's I think it might also be in the vector calculus revision at the beginning. And then we did a slides on vector calculus revision. I think it had conversions between the different coordinate systems. Okay, anyway, it comes out to be cos theta times AR minus sine theta times A theta. Okay, so that's what AZ is in the spherical coordinate systems. Okay, so we end up with A of R to be this. Okay, so we need to find B and H and E eventually. So so we know that B equals the curl of A, because that that's given here on our formula sheet, but I think we went through this before that. This is how we define A and B. Okay, and we can see that we've only got non-zero A in AR, and a theta, okay? So we just have to take the curl of A to find B. So we do have, formula sheet, we do have, the curl of a vector field in spherical coordinates, okay? We can see that, if we only got, we can see also, it doesn't depend on phi, okay? So any derivatives with respect to phi of A are going to be 0, okay? And we only have non-zero AR and A phi, okay? So if we look at this formula, we can see that, this would be 0, this is 0, okay? This is 0, this is 0, and I think we only have this term here, okay? We only have this last term that's relevant, okay? So B is going to equal 1 on R, DDR, R times the A theta component, which will be this one here, minus the AR component, the theta, okay? And it's in the A phi direction, okay? So and probably if you think of it intuitively, so the B field is going to be going around the origin, in a circular fashion. And I suppose that's a little bit intuitive if you think of a dipole equivalent to some small bit of wire that's got charges oscillating back and forth from the ends, right? Then, from your right-hand rule, you'd expect that, B field would be going around, around in a circle around the origin, okay, and would be in the A phi direction, okay? So remember, we did that for, a long thin wire, okay? So maybe that's, intuitively that sounds right, okay? So so the sign of this would, give the sign of B, but the direction would be either positive or negative in the A phi direction, right? So going backwards or left, clockwise or anti-clockwise, right? Okay. Anyway, let's do the calcs, right? So we know that B was going to equal 1 on R, dr of mu naught omega P cos omega T minus R on C times cos of theta divided by 4 pi minus dd theta. It's going to be a plus because we've got a minus here. Mu naught omega P cos omega T minus R on C sine of theta from 4 pi R. Okay, so that would be going to be 1 on R times mu naught. Okay, so we're going to have omega squared P because we're going to take the derivative of cos. It's going to be sine, will be one negative sign there. Okay, and then we'll also have an omega on minus omega on C due to the chain law, okay, going through the cos, okay, so it'll be 4 pi C, and then that will make that plus again, okay, is that right? And then for this one, it's going to be, it's just with respect to the theta, okay, so it's just going to be basically this omega P sine, it's minus sine, huh? Is that right? Yeah. Oh, yeah, no, sorry, it's with respect to, you're right, T minus R on C cos theta 4 pi R, okay? Okay, so that's what B is, okay? It's got an R squared here because we've got an extra 1 on R coming in, okay? So B equals mu naught omega P all in the A phi direction, okay? So we do that. How do we get, using a minus sign here? This term, it should be minus R and omega, and the derivative of cos is... should have a minus sign here, and I go wrong there. I think there should be a minus sign here anyway, I think. Okay, not sure why that's wrong. Yeah, sorry. So this is outside. Okay, so we're doing, so that's the derivative with respect to R of mu naught omega P, and you times it by R here. Okay. Oh, sorry, I've got this is mixed up. So this should be a negative here. This should be negative because we took the wrong, and this will be negative there. Okay, and we have with respect to theta that becomes positive. Okay, and so that's where it comes in. Okay, so then when we do the derivative here of cos to sine, it's negative, and this one's also negative, so it stays negative. Okay, so that's correct. Okay, just so I mixed these two up. Okay, so that gives us what B is. Okay, so and from B we could find H. Okay, because we know that B equals mu naught H. Okay, so we'll see later that what we're interested in is these components that decay on as a function of 1 on R. Okay, you can see here that we've got two components to that B or H field. Okay, we have one component that drops off as 1 on R, another component that drops off as 1 on R squared. Okay, so at distances, when we go out to a long way, it's going to be this 1 on R that is the dominant B and H field. Okay, and we'll see eventually that's actually important, that these actual components that drop off as 1 on R squared don't actually contribute to the radiation going out from the dipole, and that's what we're interested in, radiation from electric dipole. Okay. Yeah. So here you see that we've only got the non-zero components are in AR and A theta. Okay, and furthermore, we see that this is not a function of phi. Okay, so anything with derivative of phi is going to be 0, right? And we don't have a component in phi, so that's 0 anyway. So this is also 0, and this is 0, right? So we're just left with that. So we've got H. We can have H equals minus, and if we're just interested in, for the moment, we'll just say we're interested in this component which drops off as 1 on R. Okay, we'll talk more about that later. Okay. Now we could also find E. Okay. We can find E from a couple of ways. Okay. We could find it, from the definition of E, with the vector and the magnetic vector potential and scalar electric potentials. Okay. And we've got A, and we can find the scalar electric potential from Lorentz gauge. Okay, because we know that the phi dt is going to be related to the magnetic. Okay? So we can put those together. Okay, and we could eventually find E. Right. Okay, it's going to be really messy, but we could do that. There's other ways we could find it. We could also, once we've got H. Okay, we can also find E from using Maxwell's equation. Okay, so if we wanted to find E, we could find it from using Ampere's law. Okay, and in this case we're in free space. Okay, so J is going to be 0, right? We're in free space, so we could find the curl of H. Okay, and that would give us the time derivative of D, and we know that that's going to be equal to psi naught dE dt. Okay, so from that way, and we'll do that now. So we know we've got H equals minus W squared P sine T minus R on C cos theta on 4 pi CR. Okay, again, and it's in the A phi direction. So again, we can look at the curl of a vector field in spherical coordinates. Okay, and we can see that we've only got an A phi component. Okay, and it depends on R and theta, but not on phi. So the only non-zero component, okay, that would be 0. This is 0. That's 0. That's 0. That's 0. So it's only this. Is it? It is theta. I think it's only where is it? It's only this component that turns out to be non-zero. Okay, if we look at it, it turns out this is the only non-zero component. Okay, this would be the only one that doesn't have that will give us a component which is also goes off as 1 on R. Okay, so we'd have two non-zero components. We've got this component here and this component here. But this component, you'd see that it has a 1 on R sine theta. Okay, so if we were to take derivative with respect to theta of this H, and we multiply by 1 on R sine theta, then you get an R squared on the bottom line for the result. Okay, and for these, we'll see later that we're really only interested in the components that go off as 1 on R. Okay, but for this component, we would have R times H of phi, which would give us, we get rid of the R on the bottom line, and we take the derivative with respect to R. Okay, and then in the end, we'd multiply by 1 on R, and that would give us a result which goes off as 1 on R. Okay, so this is the only component that we are interested in. That would give us an E field that eventually goes off as 1 on R. Okay, so we'll do that. Okay, so we've got psi naught is going to be 1 on R times d dr minus omega squared P sine omega T minus R C cos theta on 4 pi C. Okay, it's going to be in the A theta direction. Okay, and that's going to be 1 on R, and it's going to be times omega minus omega on C. Okay, so it's going to give it omega cubed P sine, and it'll be cos omega T minus R on C cos theta, and it's going to be 4 pi C squared. Okay, and it's going to be omega cubed P cos omega T minus C cos theta on 4 pi C squared R, right? And so if we multiply both sides by 1 on psi naught and then integrate with respect to time, we're going to get E. So we're going to have E equals, and if we integrate this with respect to time, it's going to be sine divided by omega, right? Okay, so it's going to give us omega squared P sine omega T minus R on C cos theta on 4 pi C squared psi naught R. Okay, in the A theta direction. Okay, hope it's right. Oops, missing a minus here. We also got a minus sign here that has to come in. Yep, so there's to be an extra minus sign there. Okay, so that's the E field. Okay, so we get that, and you can see here that is indeed what we get. Okay, so we've got the E field and the H field, or the components of it that drop off as 1 on R. Okay, and we can see a couple of things. We can see that they're orthogonal. Okay, you can see that one's in the A theta direction, and the H field's in the A phi direction. Okay, so that's important as well. Okay, the 1 and R components are, okay, which are the ones which we're interested in, okay. So, if we were to plot, these things as a function of distance, then, you can see that, 1 and R drops off, 1 and R squared and 1 and R cubed drop off a lot bigger than 1 and R, okay. And, we call, these components that, drop off as 1 and R, that they're either called, the far field components or the radiation components or the radiating components of the electric field, okay? So there's two names, they mean the same thing, the radiation component and the far field component, or the far field E field, or the far field, or the radiation E field. They are the components that of the E field and the B field which drop off as 1 and R. These components that drop off as 1 and R squared and 1 and R cubed, they're called the near field components, okay? So these radiated or far field components are the components that, play a role in radio communications. Okay? They actually transmit. We'll see shortly that they're the only parts that transmit energy over distance. These near field components do play a role, but in things like transformers, induction, and the sort of things like when you use your card to open doors and stuff like that, or pay at IFPOS in the shops. That's using generally these near field components. Okay, so they drop off really quickly with distance. Okay, so shortly we'll talk more about these radiated components. We'll just also briefly touch on, it won't be in the exam, but we'll talk about the field lines. Okay, so we have our dipole here, plus and minus, and it's oscillating. We could talk about mapping or drawing contours of that represent lines of equal E field magnitude. Okay, so and it would turn out it would look something like this. Okay, so it's meant to be symmetrical, but you'd have the E field, and these lines would be representing a constant E field. Okay, and the actual direction of the E field is tangential to these lines. Okay, so at this point in the middle, E field is going vertically down because it's in the A phi direction, okay? A theta direction. Okay, so we can do that. Okay, and we can calculate those lines. Okay? They happen to satisfy this, and we can actually look at how the E field evolves over time. Okay, and there's actually a script on the LMS. Okay, so this is looking at a plane. This is looking at the XZ plane. So we're looking at a plane containing the Z-axis and the X-axis. Okay, and we're looking at these field lines in that plane. Okay, so I'll just show you that. Can we bring up here we are? Try and bring the these displays will come up. There we go. And it's in the it's on the LMS, so you can run this script. Here we go. Here. So this is plotting those contours of constant E field as they evolve over time, right? I don't know why it's coming up funny like that, but anyway, you can see that initially initially they start off I run it again. Initially they start off at attached to the dipole, okay? But then you can see that they break away from the dipole and start extending out into space and propagating as positive and negative magnitudes, okay? So you can see that this dipole is starting to generate these electromagnetic waves that are flowing out to space around it, okay? Because as I said, these contour lines represent constant E field magnitude, lines of constant E field magnitude, okay? So you can see that the E field's probably going down here, and then coming up and going down, and coming up and going down, okay? And you see as you get further away, the radius is getting bigger and bigger, expanding out in a circular direction. Eventually, when you're a long way away, and you're looking at this point, it might look like a plane wave hitting you, in the approximation, because the radius of curvature is very large, okay, if you're lots away, okay? So you can see how a dipole can be used to generate electromagnetic radiation. Eventually, the E field lines break off from the dipole and no longer connected; they're just flowing away out into space. Okay, presentation. Okay. So we're interested in these components of the field that are going off as 1 and R, because we want to see we're interested in what happens at a long distance from the dipole. Okay, and we see that the E and H field are orthogonal to each other. Okay, one's in the A phi and one's in the A theta direction. Okay, and they're propagating at speed c. If we look at omega t minus r on c, so these are sinusoidal waves propagating through space with the speed of light. Okay, which what we'd expect. Okay, mutually right angles to each other, and we call when we have a propagating wave through space with the electric and magnetic fields perpendicular to each other, we call that transverse electromagnetic wave. Okay, we'll see in a moment that the direction of propagation is in AR. The direction in propagation is in AR because of this R here. Okay, which is distance. So you've got a position vector r, could be coming out from the side or going up a bit. But as r increases, this magnitude of r increases, and so the actual propagation direction is in the direction of r. Okay, and this a theta and a phi are always perpendicular to r, right? Okay, so that's why it's called a transverse magnetic wave. Okay, transverse electromagnetic wave. Sorry. You can also have transverse electric and transverse magnetic, but we won't deal with them in this course. But they're where just one of the components, the electric or the H field, is perpendicular to the direction of propagation. Okay, so we will deal here with only transverse electromagnetic waves, TEM. Okay, you can also look at something called the wave impedance. Okay, so we could look at the magnitude of E naught and H naught, and we could divide them. Okay, so and that comes out to be a number. Okay, if you go back and plug in the numbers, you'll eventually end up with 1 on epsilon naught C, which ends up to be the square root of mu naught on epsilon naught. Okay, and that's called the impedance of free space. Okay, and work it out. It's about 377 ohms. Okay, based on what mu naught and epsilon naught are. Okay, if you weren't in free space, then this would be something different to have mu r and epsilon r coming into this. But in free space, it's about 377 ohms, and that always gives the ratio of the E and H fields, or the magnitudes of the E and H fields for a transverse electromagnetic propagating wave free space. Okay, you should know that. We can also look at the pointing vector. Okay, so we might want to find the pointing vector, because remember we said that the pointing vector equals E cross H. Okay, which gives us the direction of energy flow. Okay, so we know that E is in the a theta direction. Okay, and we know that H is in the a phi direction. Okay, so if we look up our formula sheet, that means that that P is in the AR direction. Okay, P is going to be in the AR direction. So the direction of energy flow is going to be in the radial direction out from the source. Okay, for these radiated fields or far fields. Okay, so energy is radiating out away from the dipole in the radial direction. Okay, and the magnitude, it's just going to be the multiplication of the magnitude of E and H. It's going to be given something like this. Okay, we'll talk more about in the next lecture about doing the time average of that. Okay, and getting the time average of the actual energy that's radiating out from a dipole and also over the whole sphere. Okay, so looking at the total energy that radiates out from a dipole at distance. Okay, so we'll talk more about that next time. Okay, and then we'll also have a quick look at extended line radiators. Okay, so any questions on that? We'll end up there. So I think in the prac classes you also deal with this week. Okay, so if you haven't had your prac class yet, you'll be able to know a bit more about what it covers today. Okay, thanks very much for coming.